Welcome to the Power Control Unit, PWRCU chapter of the HT32 MCU basic tutorial. This chapter will introduce the HT32 MCU Power Control Unit, PWRCU. The following will introduce from 5 aspects: Power Control Unit Introduction, Power Domain Distribution Structure, Power Supply Monitor, Power Saving Modes, and an application example. Part 1, Power Control Unit Introduction. Power supply is the basis to ensure the system's stable operation. Power consumption is regarded as an important issue in embedded system applications. Facing the power consumption of the device, we can reduce power consumption by using the power control. The HT32 MCUs include an Integrated Power Control Unit, PWRCU. It is used to monitor the power supply and manage the device's operating modes to ensure proper system operation, reduce the device's power consumption, and improve the device's battery life. Next, we will briefly introduce the features of the HT32 MCU PWRCU. The PWRCU is divided into 3 power domains, provides 4 power saving modes, and includes an integrated 1.5V LDO and depletion MOSFET. The PWRCU also supports brownout detection and 8-level programmable low voltage detection, and provides 40 bytes backup domain registers for data storage. Part 2, Power Domain Distribution Structure. In order to facilitate power management, the VDD power domain, V-core power domain and backup power domain are provided according to the functions of HT32 MCU core and its peripherals. The VDD power domain is powered directly from the VDD and VSS pins and supplies power to the internal LDO, DMOs, and IOs, etc. The V-core power domain is powered by the internal LDO in the VDD domain and supplies power to the CPU, memories, APB INTF and digital peripheral. Backup power domain. When VDD is powered on, the backup area is powered by VDD. When VDD is powered down and the V-core power is cut off, the backup area is continuously powered by VBAT, which is used to retain the contents of the backup registers and to maintain functions such as RTC. Part 3, Power Supply Monitor. By detecting the external VDD voltage, the PWRCU Power Supply Monitor provides the power monitoring, reset and power down emergency handling functions to ensure the system reliable operation. The VDD power domain has an integrated POR and PDR circuit module for power reset generation. When VDD continues to rise to greater than VPOR, a power on reset signal is generated. After a time of TRSTD, the MCU starts to normally operate. During normal operation of the MCU, when the VDD drops to lower than VPDR, the MCU will enter the power down reset state. The low voltage detector, LVD, can detect whether the supply voltage VDD is lower than a programmable threshold voltage VLVD. It is selected by the LVDS bits in the LVD-CSR register. When a low voltage on the VDD power pin is detected, an interrupt and an wake-up event will be generated. The brownout detector, BOD, is used to detect if the VDD supply voltage is equal to or lower than VBOD. When the VDD supply voltage is lower than VBOD, the PWRCU will regard this as a power down reset situation, and then immediately disable the internal LDO regulator or issue an interrupt to notify the CPU to execute a power down procedure. Part 4, Power Saving Modes. Power saving mode is used to reduce the power consumption of the integrated circuit. HT32 MCUs support 4 power saving modes: sleep mode, Deep Sleep 1 mode, Deep Sleep 2 mode and Power Down mode. In the sleep mode, only the CPU clock is off and the CPU stops operating, but the peripherals are enabled. Disable the peripheral clock can reduce power consumption. The system will exit from the sleep mode and resume normal operation via any interrupt or wake-up event trigger. In the Deep Sleep 1 mode, all clocks in the V-core power domain are off, HSI, HSE and PLL are disabled. The high-speed oscillator stops oscillating. Turn the LDO into low current mode to reduce current in the V-core power domain. The MCU exits this mode via any EXTI event or comparator, RTC, LVD, wake-up, USB, etc. Signals to resume the normal operation mode. In the Deep Sleep 2 mode, all clocks in the V-core power domain are off and the CPU stops operating. HSI, HSE and PLL are disabled. The high-speed oscillator stops oscillating. Use depletion modes to reduce current in the V-core power domain. The system resumes normal operation mode only when the MCU is woken up by RTC, LVD or wake-up signal. Some MCUs support EXTI wake-up function. In the power down mode, V-core power domain is off. Reserve VDD in backup power domains for power, oscillators and all clocks are off. CPU and all peripherals are disabled. Internal RAM and register contents are lost. Only the registers in the backup domain are saved. When the MCU is woken up from power down mode, the PDF bit will be set, a 1.5 volt power on reset will occur, and the MCU will re-execute the program. The system will resume normal operation mode only when the MCU is woken up by RTC, LVD, wake-up or NRST signal. It is noted that when exiting from deep sleep mode, the HT32 MCU will first use HSI as the system clock until the initial clock source used before entering deep sleep mode stabilizes. In addition, a 1.5 volt power on reset will occur soon after the system is woken up from power down mode, and the HSI oscillator will be used as the system clock at this time. The differences between the four power-saving modes of the HT32 MCU PWRCU can be described in terms of power consumption, wake-up time, and wake-up source. The four power-saving modes supported by PWRCU are progressive. Each time the MCU enters a deeper power-saving mode, the fewer the clocks or functions the MCU operates. The wake-up sources will be reduced, the power-saving effect will be improved, and the wake-up time will be longer. Users can select specific power-saving modes based on their application requirements to optimize the balance between low power consumption, short wake-up times, and available wake-up sources. In the above power-saving modes, if the backup domain is normally powered, the RTC in the backup domain will operate normally, and the registers in the backup domain will be stored without being affected by the power consumption mode. Power-saving modes are important for implementing low-power designs. When entering power-saving modes, the MCU must call a WFI or WFE instruction. WFI, wait for interrupt, it means wake up by waiting for interrupt. WFE, wait for event, it means wake up by event. They are essentially CPU instructions and are encapsulated as functions in the library file. The following are some of the PWRCU related functions. The first function is used to enter the sleep mode. The second function is used to enter the Deep Sleep 1 mode. The third function is used to enter the Deep Sleep 2 mode. The fourth function is used to enter the Power Down mode. The fifth function is used to enable or disable the external wake-up pin function. The sixth function is used to enable or disable the RTC wake-up source. The seventh function is used to enable or disable the RTC interrupt source. The eighth function is used to configure the EXTI channel X event wake-up function. The ninth function is used to enable or disable the EXTI channel X event wake-up interrupt. The 10th function is used to clear the EXTI channel X wake-up flag. The 11th function is used to configure the LVD voltage level. The 12th function is used to enable or disable the LVD event wake-up function. The 13th function is used to enable or disable the LVD wake-up interrupt function. The 14th function is used to wait for the PWRCU to be accessed. The 15th function is used to get the PWRCU state flag. Finally, we will summarize the learning content by using an application example. The example is a Deep Sleep Mode 1 program from the standard firmware library PWRCU. It should be used with the HT32F52352 hardware starter kit and the ESK322X001A expansion board. When the key 1 has been pressed and the program starts, the LEDs will turn on and off regularly, where the LEDs are off when the MCU is in Deep Sleep 1 mode, and the LED 1 is on when the MCU is being woken up. The execution flow of the program is as follows. The system first turns off LED 1, LED 2, and LED 3, and then enters Deep Sleep Mode 1, waiting for a wake-up signal. When a wake-up occurs, it immediately enters the interrupt service function. If awakened by the RTC, LED 3 will be lit. If awakened by key 1 EXTI, LED 2 will be lit. After exiting the interrupt service routine, LED 1 will be lit. The program will continuously execute in accordance with the above flow. It is noted that when the HT32 MCU enters a power-saving mode, the debugger cannot be connected to the HT32 MCU. The MCU must be woken up before using the debugger. The following is a part of the sample procedure. The user presses the key 1 to confirm that the MCU enters Deep Sleep 1 mode. Set the RTC as a wake-up source. Set the key 1 EXTI as a wake-up source. Set the LED 1, LED 2, and LED 3 to be off. Enter the Deep Sleep 1 mode and set WFI to wait for an interrupt to wake up. When a wake-up interrupt occurs, the system will immediately enter the interrupt service routine. If awakened by the RTC, LED 3 will be illuminated. If awakened by key 1 EXTI, LED 2 will be illuminated. After exiting the interrupt service routine, the program will continue executing the program following the WFI instruction, which is to illuminate LED 1. The program will execute in a loop, turning off LED 1, LED 2, and LED 3 again after waking up, entering Deep Sleep Mode 1, and waiting for a wake-up. Holtec has a professional service team to assist in the development, design, and after-sales service. Welcome to contact our business unit for more detailed product information and consulting services.